Swayam Prabha. Digital India. Educated India.
I made this topic as my research activities at Geoenvironmental Engineering Laboratory at IIT Madras, rather talking about only one carbon sequestration. Of course, my technical talk is on the carbon sequestration, but I wish to really, spend some more time on other activities as well. In this particular group, how many are civil engineers? Very good. That means that now I can talk all nonsense about civil engineering and so that others will not really notice. Am I correct? No. In general, there is no difference between a civil engineering, chemical engineering once you cross certain limit. You will see that a lot of things what we do is so called in civil engineering. But you will not really see that why civil engineers are unnecessarily jumping into chemical engineering aspects. Why these guys are eating our money. And then you may be thinking in that direction as well. Let us not really worry too much about it. In general, I talk about my research group, all the work. I am only the communicator here. Please note that these are not my slides. This is the hard work of every PhD student. I am just only communicating their views and their ideas, rather proposing my own ideas. Let me keep it like this. If you like the slides and then the credit goes to me, if something wrong, and this is up to them. So today's major work is basically one of the scholar, Dr. Kumba Mutlangwar, who did substantial work in the area of sequestration. That part I am really going to discuss. Apart from that, my group also talk about since inception, we are more focusing on the design of liners. How to contain the waste, whether it will be hazardous waste or non-hazardous waste, including the radioactive waste. You will try to see that one. We basically design a barriers, buffers, systems in order to contain these waste. Second aspect is, as a civil engineer, we have some problems related to the soils because we are more worried about strength of a soil or permeability of a soil, porous nature of the soil. But there is an issue with this. Some of the soils earlier, if something is declared unsuitable for construction, we used to ignore that site, we used to move forward. Now there is no luxury of moving forward. What are the site you have? And an example, if there is a small tiny plot you have right adjacent to the Peringudi dump site, you have no choice other than constructing there. But these sites are not really good for construction purposes. They may not have enough strength. We need to stabilize them. How to stabilize them? Conventionally, people use a lot of chemicals like a lime and then cement. Our group also worked on the lime and cement stabilization. Many times, these conventional techniques may not be sufficient and then we may have to really go for some of the electrokinetics, applying the current, try to pull out the water or maybe the contaminants out of it. Many times, we also use biopolymers to stabilize them to enhance one particular property of a soil. Recently, we are now focusing more on the how best we can able to deploy or employ bacteria in order to strengthen the soil. You will be trying to discussing about all those biochemical processes also a little bit, how to strengthen the soil and how to really get it off. Further, we are also working on some of the biochemical processes. We isolated some bacteria which can able to really consume or digest methane emission from the landfills or dump sites. So we can convert this methane, which cannot be really captured economically for the fuel purposes, but we can able to minimize the greenhouse gas effect of all these things by just converting the methane into the biodiesel. That's the one aspect. The last one, is a geochemical, the geological sequestration. I will try to dwell on that little more in detail, so I will not really focus more. Further, we also design certain, permeation of contaminants through a compacted clay liners or geosynthetic clay liners, or maybe for that matter, we also talk about contaminant transport through the high density polyethylene geomembranes. So this is the basic overview of my work at IIT Madras. I will dwell on individual things later on. First, let us try to focus more on the geological sequestration of carbon dioxide or greenhouse gases. In this particular case, we only talk about the carbon dioxide. Now, what is primary importance? You have so much to do when you are really talking about a greenhouse gas mitigation. There are various techniques you can able to do at a small scale level. But all these techniques existing at this point of time may not able to address what we emit 100%. So one such way is as a geological engineer or maybe as a geoengineer, can we able to capture the carbon dioxide at the source, transport it to the suitable site, dispose into the underground deep geological media. This is one way of doing this. But if you look at this particular one, why this really arised? You all know that I need not really explain this, but there is a constant gradual increase of the concentration of the CO2. So one side I am really talking about emissions in gigatons, second side I am just talking about concentration in ppm. If we don't really do anything, this will touch 700 ppm very soon. That soon somebody will decide. Let us not really worry. But now if this is a scenario, this is happened due to so many things, you may say that industrialization, you may say that economic growth, deforestation, even agricultural practices even. Or maybe building of urbanization of so many things. But the consequences are very, very clear. Whatever may be the reason, let us not really blame anybody. But the consequences are very, very clear. Global overall temperature is increasing. Somebody says that, okay, this is something like a melting of ice. Somebody says that, the recent floods also related to that. Somebody else says that, extreme weather conditions. Extreme doesn't mean that always rainy. It could be something like this as well, a drought as well, wildfires, so many other things. I am not really here to just address any one of them. Let the reason may be the something, but one thing is very, very clear that the concentration of carbon dioxide should be limited. Can we able to do that? If at all we want to really do that, there are so many ways, as you know, that terrestrial type of a carbon sequestration that will also account for a little bit. A lot of people talked about, can we dispose everything into the ocean? That was the initial fancy idea. If you can able to do that, maybe, your source and sink terms may be quite apart. It may not be feasible some places. Even if it is feasible, it is going to alter the ocean ecology drastically. Acidifying the ocean may not be a good idea. It will have a lot of other implications. Let us not really do that. People just stopped it at a conceptual idea point of view. Little bit one or two, a prototype studies people did, and then they didn't really go for. The second option is maybe the last option. Geologically, can be able to store them for a long period. It may not be a permanent solution. I don't want to say that is a permanent solution. Till you have a solution which is really can be implemented in large scale, can be able to store this entire carbon dioxide into the deep geological media, for example, say a sedimentary basin or a saline aquifer, where which is not really useful. I am really talking about 500 to 1 kilometer down below the ground surface. Alright. If you are really pumping such kind of a scenario, what is really going to happen? We need to understand the kind of layering system from the top to the bottom. Even if you are really disposing at that particular depth, there is no guarantee that it will be stay there. It will escape through the fractures. It will escape through the so many other ways, pathways. And finally, whatever you are supposed to really mitigate, you are not really addressing the problem. Now, if this is the scenario, we want to really understand how best we can able to use a certain sink media to dispose the carbon dioxide, how the gas is really going to interact in that kind of conditions, and then how we can able to ensure there is no possibility of leakage and there is no possibility of, some people say that if you are doing that, there may be a possibility of tremors, there is a possibility of earthquakes, there is a possibility of entire thing will get collapsed, and so many other issues. Can we able to really demonstrate scientifically or not? This is basically what we wish to really do that. As I mentioned earlier, among all other techniques, we want to really use, you take the carbon dioxide from the source and then put it down below into the geological media, 500 to 600 meters or maybe at least 1 kilometer down below, where the groundwater at that particular location probably saline in nature. You are not really spoiling any groundwater. Now, if you look back, what happens to this one? This is the reservoir. If you look at the scale point of view, tens of kilometers, maybe the reservoir may be thousands of kilometers. Just schematically I have shown here. On top of that, there is a different layers here. If you can see this one, there is one kind of a cap rock. Then there may be an intermittent layer as well, and then cap rock. Cap rock means whatever the layer sitting above the reservoir, which can able to provide a containment to this particular system. This cap rock is no more like a intact, like a solid steel kind of a plate. Don't really imagine that. It will have a fractures, it will have a faults, it will have so many other things. Now let us try to idealize the situation little bit further. Suppose if this kind of scenario, if you are disposing through this injection well here, there is a fracture, it will migrate up to this point. If there is another fracture, it will migrate up to this point, it will further migrate and then just keep going. But these fractures are not just simple tiny voids, just not like a opening that where it is escaping through. These gaps also is filled with a certain type of a geological materials. Let us imagine that if these kind of a gaps are the cap rocks, majority of the cap rocks are made up of shale. Then if you look back, the mineralogical composition of that kind of a material is basically clay type soil. The clay minerals may be 60 to 70%. Remaining may be a non-clay minerals, something like a quartz, which is very inactive. Fundamentally, what really happens when the gas is just interacting with the clay type minerals and non-clay type minerals? Do you have any difference fundamentally? Now try to imagine that there is a fault filled with these minerals. You are injecting the gas from the bottom. The gas will try to migrate slowly, and then this migration can able to really see something like this. Am I right? Now, if this migration is really a mere physical phenomena, or something else is also going to happen, that part you need to really see. What people have noticed is when the gas is at such a very high pressure. Why high pressure? We are really talking about 5 to 600 meters down below the ground surface, where the pore fluid itself will be at a very high pressure. At the same time, when we want to really pump in this kind of a carbon dioxide, we need to really make the gas to the almost supercritical state, so that the density and viscosity will enable us to really pump very easily, right? That means that under such high pressure, the temperatures also, the geothermal gradient will be there. There will be a certain amount of change in temperatures also there. So when this kind of an interaction is happening at a high pressure and then elevated temperatures, not very high, but up to very close to 55-60 degrees, quite possible, 35 to 50-60 degree. Under this condition, the clay minerals, certain type of clay minerals, what they exhibit is they absorb the CO2. Upon absorption, they do swell, the way they are swelling upon absorption of water. When they are swelling, what really happens is, it's a good phenomena, one way that all the fractures might get sealed. The self-sealing ability may be there. Sometimes it is not only that, if it is keep on expanding, what will happen? It also exerts a lot of pressures on the entire fault. If you are really exhibiting a lot of pressure, if you are crossing the threshold value, eventually you will fail. We don't want to really see such kind of a scenario. So that means that the overall idea is, can we able to strategically adopt the injection strategy so that we don't really encounter such kind of scenario. That means that in order to do this, we should have two things. One is, what is the absorption ability of this kind of a clay mineral, and then the resulting swelling. The resulting swelling, how much change in the stress, whether this stress is really causing any kind of a failure or not. So that means that experimentally you measure something, you have to build a numerical model by accommodating all this hydromechanical behavior in a coupled way, then only you can able to really do the little bit of a justice for this. So when you are trying to do that one, the first part of this one is, we try to assess. Imagine that this is also again another hypothetical situation. Most of the shales may have some amount of the 2:1 minerals. Suppose these 2:1 minerals also may have a different exchangeable cations in their position. In the laboratory, we try to simulate the same condition. We try to homogenize the clay with a sodium as an exchangeable ion, potassium and as well as calcium. The specific surface area has been measured by using the BAT method. Then we know their hydrated radius. The ionic potential is basically ratio of the valency to the hydrated radius. Does it have any impact on the adsorption capacity or not? Alright. But when you want to really measure the absorption capacity of a given clay, we need to really initially degas the clay in a equipment. You need to really preheat it. Whether the preheating can be done at 200 degree or 300 degree or 400 degree, that we cannot decide randomly. Rather, let us try to get their thermal decomposition profile by using a TZA. Then you look at it, there is a peak here, it's another peak, third peak, fourth peak. Then if you look at it, the first peak represents the free water, bound water, leaves the clay material when you heat it in the range of 180 to 200 degree. If you cross further, strongly brown water will go. If you do it further, the clay itself will decompose after beyond certain time. So we don't want to disturb the structure of the clay. Our intention is to really get away the bound water, so that we will understand the material's behavior little better way, so that we don't complicate the presence of water, non-present, absence of water. So then we try to understand the degassing temperature is very close to the 150 to 180 degree. That part we have done. After doing this, we bring the sample to the high pressure gas analyzer. It is a very small tiny equipment where you will place the specimen here, degas it to the desired level, then you inject the CO2 at different pressures. Then you try to measure how much get absorbed. Now you try to understand this in this entire process, you will only get a experimentally measured adsorption capacity. This is called as a excess adsorption capacity. Then this we try to see for a different clay type materials, then over a different range of temperatures. If you look at it, one thing is very clear, the excess absorption is going to change the moment you change the type of the exchangeable ion. It is also changing with respect to the temperature. Right? Now by knowing this particular fact, now this is what exactly I try to mention. This is because of the interlayer cation type is going to decide basically the adsorption value. Once you know this, can we able to model this one by using any one of the theoretical models? For this purpose, we use the one-Oquendo model. Then we try to back calculate the parameters related to one is related to the capacity C, second one is related to basically the fluid solid, the energy parameter EFS, and these values are just captured. Then try to compare with respect to the BET or ionic potential, what I have shown earlier. Then further we also seen how these are all varying with respect to the temperature. So we validated this data by using the experimentally measured or reported values in the literature. Once you have done this, now you are pretty much sure about your measurements by using the high pressure sorption analyzer. So after doing that, what basically interested is the excess isotherm is not a really good term for you to capture, because that's not a true representative. You need to convert this experimentally measured excess isotherm into the absolute isotherm so that your modeling can be better. So in order to do this, we have to assume certain kind of a, the density of this adsorbable fluid. Then we try to vary with the different, concepts, whether reciprocal of the van der Waal or the liquid density approximation or the critical density approximation. You try to compare with the experimentally measured value. After doing that anyway, these are all better way that one particular concept is better, we can try to do that. Further what we did is, we try to observe the absolute isotherm what you estimated by using the various theoretical models. For example, in this case a Langmuir fit I did, and second one is DA fit. Is that Langmuir can able to really fit over a range of pressures? The answer may be no. Then otherwise you have to really go for another model, which is basically DA fit. So by doing this, and what we did is, finally we got some of the terms related to the how much adsorption by the micropore filling, what is the characteristic energy, and then so many other things we try to capture for different clays over a different temperatures. This part is done. After doing this, this is what exactly you will have at the end of the part 1. So now we capture the adsorption behavior of the material over a range of temperatures or a range of pressures what we anticipate in the geological sequestration. Now how to take this information into the carbon dioxide sequestration into the geological media? Can we able to develop a mathematical model or not? That's what the basic idea. Now the second one, anyway, the hysteric heat also we try to compare so that it can able to isosteric heat. It can able to say that whether it is a physics option or chemistry option. So mostly predominantly in the for the material what we consider is the only physics option. Double layer adsorption happened. So we could able to capture the entire phenomena very neat and clean way. So this is the basically how the absorbed phase density, this is only is varying with respect to pressure, as you know. That's why that's one of the difficulty that why we could not really use the excessive isotherm, sorption isotherm, because this guy is varying. So then with this we try to capture the absolute isotherm for a given type of a material. This is the one way of looking at. The next part is something to do with this. Can we take the carbon dioxide into the deep geological media? Now the clay is filled in the fault. If it is exposed to the different pressures and temperatures, how it is really going to respond? Let us try to understand that. Imagine that there is a only pure clay alone, or maybe the pure clay and quartz available, which is in a dry state. When you expose this kind of a system to the high pressure of CO2, possibly two things can happen. Once I told you that because of the adsorption of the CO2 on the clay mineral, swelling took place. If you don't allow the swelling to freely happen, strain will develop. Once the staining of the material is happening, stress is going to develop. If the increase in stress is going to cause a failure, then it may fail by two mechanisms. One is by shear, second one is by the hydrofracture. So these two things we need to really capture very clearly. So for this purpose, the mathematically three models developed by Kumba, I am just going to present here. One is the volume expansion of the clay mineral itself will take place upon absorption. Now between the clay minerals there is a pore. You are pumping the gas at such a high pressure. There is a poroelastic strain as well. That guy will try to compress the particle. Other guy will try to expand the particle. These two counteracting phenomena will finally change the porosity of the material. If the porosity of the material is changing, you know that the permeability is going to change and so many other parameters are going to change. Now our job is overall after considering the effect of the adsorbed induced strain, the effect of the poroelastic strain, finally the combined effect is somewhere here. Alright. In order to do this, what we did is simply we try to club in the adsorption induced strain, which is ES, is superimposed onto the here. If without this, there is no adsorption induced strain. With that, we can able to do that. For that, further, we also wrote a equation for the mass flow equations as well as in a coupled way the stress equilibrium equations. You try to write it. So basically, one common term here is the phi is going to talk about a coupled variation. If the adsorption increases, porosity changes. You try to couple it between these two equations. At the same time, the bulk modulus what you have here, and then in terms of the displacement, you try to couple it. So this model is only talking about a single phase system where the solid, where the gas is interacting to each other. Nothing more than that. Now with this, if you can able to really solve these equations by using a Langmuir isotherm for the swelling or maybe adsorption phenomena point of view, then you may get some variation. Before taking the model to the further, what we did is we calibrated the model by using the experimental data reported by Zhang. What he reported is something called swelling pressure. Second one is the pore pressure. Both we try to calibrate it our model. This is the experimental data by Zhang. These are basically by our numerical model. After doing this, if you look at this particular entire data, now this is where the injection happens. This is a reservoir, this is a cap rock, where the cap rock is having some kind of a fault or whatever it may be. It may escape through this. We are trying to model this zone. Now if you look at this particular zone, there are different stress state conditions may prevail there. One is, for example, completely confined. That means that the clay is not allowed to really, swelling is happening, but you don't allow the clay to change its dimension. You are constraining. That's one possible way. That means that at a greater depth of 500 to 600 meter down below, you will not have a, you will have a confining effect. There is a second one is possibly a free condition that the clay can freely swell. There are no constraints. So that's why the side one we put a roller. The injection is happening at the bottom. The top will try to swell freely without having any constraint. Fourth one, it may not be in between both of them. There may be a kind of a scenario called uniaxial, where example at 500 meter down below, we know that the overburden pressure is in the range of very close to 40 megapascal. If this 40 megapascal is placed here, how the clay is really swell under that kind of a pressure? What are the changes in the stresses? This is what basically we want to really talk about, these three conditions simultaneously. When you are really looking at this particular one, the first one you see, this one is with absorption induced strain. That means swelling is considered, absorption is happening, swelling is happening. In this case, there is no swelling. Just I want to compare with swelling, without swelling. That means this is only the poroelastic strain. These are basically combined of both. One thing is very, very clear, the change in porosity and permeability ratio. So basically the porosity variation we captured, we try to correlate in terms of the cubic term, in terms of the permeability value. So this is very, very clear under confining conditions. This porosity variation, the permeability ratio variation is not too much, because you are not really allowing the clay to expand too much, you are constraining. Then as a result of the swelling take place, even though what of changes happens due to the poroelastic effect as well as the adsorption strain induced effect maybe get counterbalanced equally, then this is really one scenario. There is another scenario, you try to look at it, it is that basically a free condition. You see, completely allowed freely, the permeability ratio changed drastically by almost 20%. When permeability changes by 20%, escape rate is very high. Right? Let us try to see that impact of all the things, and then can be able to really capture in terms of this one. Our ultimate goal is to see how the permeability is varying. Second goal is to see the change in stresses due to the poroelastic effect as well as the adsorption induced strain effect. Can we able to really capture the change in compressive stresses? The compressive stresses also vary, depends on the kind of a condition what you impose. Right? If you are imposing a confined condition, there is a lot of change. That means potentially you are traversing towards existing equilibrium condition towards the failure, or maybe may not be also. Alright. So with this we have really closed the first model, validated the model, that's perfectly alright. But the problem with the Langmuir isotherm, it will only represent the small range of pressures, the adsorption behavior. But in general, in the field, you pump the gas at a supercritical state. When you are pumping at a supercritical state, the Langmuir isotherm may not really able to capture the entire phenomena, because fundamentally the volumetric strain, or maybe adsorption also for that matter, increases, reaches the peak value, thereafter it decreases. Then what we did is, one of the field scale study we adopted, where people try to pump in the gas at a different pressures in a step function, then make it a equilibrium, and then keep on increasing till the equilibrium. Then we try to capture the linear strain by using our model, and then as well as the volumetric strains. So with this, we could able to really validate our model even for the field level representation. Now by doing this, can we take the model little bit further? Can we say that the change in porosity, the change in compressive stresses, will it lead to the failure or not? That's what the basic question is. For that matter, the Rehnquist, proposed two hypotheses. One is a shear failure, the first one. The second one is by the hydraulic fracture failure. He gave the condition that he tried to define if the pressure developed within the system, when you compare with respect to the critical pressure, the pressure margin, the PSM, is a pressure and then critical pressure if you try to see. Whenever it is becoming a negative, it is safe. That means your pressure is lower than the critical pressure, it is safe. Whenever it is becoming a positive, it is unsafe. Unsafe doesn't mean that you are going to really fail everything. Just don't really take it a direct conclusion, right? So these are the two ways that how to really get these two things. Then with that, we try to consider a 2 meter thick a representative cap rock. How it is really going to change? We are injecting from the bottom. We purposefully not really deviated this bottom zone or demarcated this. What we did is we try to observe the variation of the along the height, how the pressure margin is really changing. If the pressure margin is towards this side, it's basically negative, it's a safe. That means that the bottom portion of the cap rock still in the safe zone, but the top portion of the cap rock is moving towards the unsafe. Now with this, there are two things. One is for the slip, onset slip. Second one is for this one. These are shear failure, and this is basically hydraulic fracturing. So that means that two are independent phenomena by which the material can fail. But the story here is, in this case, in the slip, the top zone is more vulnerable than the bottom zone. But when we are really talking about this one, because anyway the gas has to really migrate all the way up to this, it will take a lot of time. So with respect to time also, it's not really happening. So in this way, we could able to really capture the variation of stresses within the system, whether it lead to the failure or not. Further, we also did, in one case, at different depths, the initial condition of the stress state may not be same, meaning thereby the vertical overburden pressure sigma V in this direction, the sigma H acting in the other direction may vary. What we did is the ratio of these two stress states we try to consider. We vary it numerically. Can we able to really capture the phenomena? Do we see any other entirely different scenario? We try to see for the both hydrofracturing as well as other one very clearly. So with this, we saw that the more or less behavior is same. There is nothing much is really going to happen. Can we able to really take this model a little bit further? Now, can you introduce into this model is a two-phase system where your clay alone is not only dry condition, where it is interacting with the CO2. You can also introduce some kind of a moisture into the system, which is in general possible. It may not be completely something like a fully saturated condition, but it may be 1 or 2 layers of a molecular layers or 4 molecular or 10 molecular layers of water will be there. The previous model is not really able to really capture that phenomena. Now we modified that behavior by incorporating 2 additional terms. How? The moment you introduce the second phase, the capillarity comes into picture. When the capillarity is there, it is going to induce a suction into it. That means that when you are pumping a gas in a saturated, partially saturated media, it will drive out the moisture out of the system. When you are driving out the moisture, what really happens is the shrinkage of the specimen will take place. Right? That's one possible phenomenon. Second thing is, when you are really pushing the gas into the system, it will also absorption will take place, swelling will happen. Both shrinkage and swelling side by side can happen. It can be able to really captured by these two phenomena. Again, we went to the original governing equations. We altered these equations in order to capture for the both multi-phase system. Not multi, it's a two-phase system. Let me not really, boast it too much. With that, let us try to see how this is an injection strategy if you are really following in this particular fashion. Anyway, injection doesn't mean that we will suddenly impose 50 bar and then not like that. We will slowly, incrementally will go. Any injection strategy we try to follow. We maintain certain days. This is also as per the one of the, the field site data we have taken. Then we try to impose it. A to B we increase, B to C we maintain constant. Then slowly we happen. Now, if you look at it, whether the material is going to fail or not, in civil engineering terms, mostly, we try to consider in terms of the deviatic stress. If the deviatic stress variation is too much, it may lead to the failure. If the deviatic stress is in general is reducing, then it may not lead to the failure. If you look at it clearly, from A to B, as injection started, it increased. Whether it's touching the threshold value or not, we are not really talking at this point of time. Then B2C, when the relaxation happened, again it come back. Then again it increased. So overall, we know how to capture the deviated stress variation. Now with this, what Kumbha proposed is various different injection strategies. Whether the injection strategy is so quick or maybe so slow, or maybe what should be done. So he tried to finally came up with a set of injection strategy where we don't really introduce any kind of a failure. Our idea is not to really induce a failure. So with this, the mean effective stress variation, shear stress variation, we try to see. This is the overall story of the geological sequestration, the limited way what we did. In summary, maybe let me try to put it, even though you might have already captured it very clearly. We all know that monazite is a 2:1 smectite base mineral. Is significantly influenced by what kind of a cation is there in the exchangeable position. That part is very, very clear. Second thing is, we all know that the adsorption capacity decreases with increasing temperature. It is also varies with the exchangeable ion as well. Alright. In case of a potassium based exchangeable thing, there is a strong adsorption strength was observed due to the minimal, lateral interaction between the absorbed molecules. Anyway, we try to access isotherm, we try to model by using the Ono-Kondo model. That was really perfect, but the DA model was most accurate in order to capture the absolute isotherm. So that's the one thing. Temperature dependence also we try to capture it. We also know that based on the isosteric heat values, mostly less than 40 kilojoules per mole inverse, it's basically physics option. So it's a reversible phenomena. It's no chemical absorption as soon as you introduce the system into the CO2 into the system. Over a period of time, maybe some precipitation, some dissolution mechanisms may induce the chemical, phenomena, but at this point of time, it's a completely purely this one. Now, people ask me a question that whether when you introduce a gas at atmospheric level, that do the clay will swell? Answer is no. You need a minimum pressure at least 2.5 megapascal to initiate the CO2 induced swelling, adsorption induced swelling. In the case of a monomolecule, what we have really considered. So that means that the swelling of clays in a atmospheric level don't expect. Otherwise, you may be thinking that what will happen to my building foundation because of the rise in the CO2 concentration in the atmosphere. Nothing will happen to your building foundation. That much I can guarantee you, unless you really increase this one. Overall, we try to capture the behavior of the swelling in the form of a strain, and that strain will alter the stress distribution. Primarily, in the case of a permeability, it decreases when you are really talking about a confined condition. That's a good for you. That means earlier whatever maybe the leaky path was there, it get closed. That's the one way that. But in the free and axial conditions, of course, it will facilitate the migration of the gas, because you don't confine the system. It will swell, it will expand the void volume, and once the void volume is more, then eventually the flow is more. So finally, the adsorption induced swelling generates the compressive stresses, and then under this condition, confined condition, that is a more, and basically that may be one of the possible way that one way permeability point of view it's good confined condition, but when you are really looking at the deviated stress change point of view, it may be a little bit counter effect. So overall, this is what the story on geological sequestration of carbon dioxide. As a civil engineer, what we can able to do.